So just to begin, my goal is to kind of finish up the discussion of fluids today. And then if you have questions about fluid stuff, we can talk about it then, or we can, just ease into the last chapter, which is on kind of the kinetic side of thermal physics. And I wanted to remind you of a problem we did on a worksheet last time that had to do with a hydraulic lift. And, it's easy to sort of gloss over how amazing this is, but we've got this fluid reservoir here. It's hard to see in my scan of my solutions, but there's fluid down in here. And there's just a huge piston on this side and a very small piston on this side. And the question is, how hard do you have to push down on this, lowering that piston to lift up a 1,000 Newton car at a constant rate? So I'm going to push down on the one side. I'm going to be lifting up an entire car 1,000 Newtons. And the answer, amazingly enough, is 1 Newton. It just doesn't seems like you're getting something for free. You're not if you work out all the details, but I thought I'd show you and maybe pass around something where you could feel it with your own fingers, because it's sort of impressive, even if you're not lifting up a whole car. So here's kind of my way of making up the best I could of something similar. I've got 2 glass syringes. And, you don't run into glass syringes very often, but one of the nice things about them is they have sort of a ground interior side of the cylinder, and they're almost frictionless. Like it's a little bit dangerous, because if you turn it upside down, it'll just fall right out and could break on the table. But there's almost no friction between. Somebody must know what the name of this thing is, the plunger thing that goes into it. There's probably a technical name for that. I'll call it the plunger, for lack of a better word. There's almost no friction between the 2 cylinders. I don't know how that works, but it really is amazingly frictionless. So these 2 can go up and down with almost no friction. I've got a large diameter one here, a little bit less than 1 inch of the inner diameter there. And then this one's probably a little bit less than 1 centimeter here in diameter. And I've connected them with a tube, and I'm going to put, there's just air in there, no water or anything. And air is going to be my fluid that's in there, just like in that hydraulic lift. So I'm going to take out this plunger, connect up the tube between the 2 bottoms. I'm going to put it back in here. And amazingly, it makes a pretty airtight seal. In other words, you think the air might leak out if it's pretty frictionless, but it doesn't. And as I push this one down, this one goes up, and so on. So I've got a kind of a lift there. And you can see I have to push this one down a lot to get that one to lift a little. That's the source of the mechanical advantage. What I want you to do is, I'm going to pass this around. I've got a little brass mass here. And, just be careful not to break this, because these glass syringes are pretty expensive. You can this is going to be our car that we'll lift. And we're going to test it 2 ways. I'm going to put the mass on top of this large side, and I'm going to just judge with my finger, how hard do I have to push down to kind of hold it up? And then you're going to have to balance it a little bit carefully, because this platform up here isn't so wide. I'm going to place it on this smaller platform and kind of push on the other end. And you'll find you have to exert a relatively large force compared to what you have to do on the other side to lift the same object. So in one case, it's a small force lifts a really heavy mass. In the other case, you need a huge force to just even lift a small mass. And eventually, of course, it's not a perfect seal, and the air will leak out of there. So if you find this thing is going too far down, you can just carefully remove this from the side, take this out, connect it up like this, gently, because all these are made of glass, and then drop that back in there. And it's put some more fluid in there, because it does slowly leak out through the gap between these 2. That's Pascal's principle. Well, at least it was an application of Pascal's principle. Pascal's principle says when we increase the pressure by pushing down on one end, it increases the pressure by the same amount all through the fluid. So if it goes up by 100 pascals at one point, it goes up by 100 pascals everywhere. Okay, let's go back to the slides and see where we are. Let's see. Make sure my pointer is working. Yep, okay. So I know we talked about Archimedes' principle and the buoyant force a while ago, and we probably have a pretty good idea of how to use it, but it is a little bit non-intuitive. I would say more than half of the homework problems have to do with the buoyant force and Archimedes' principle, so it's sort of heavily represented in there. The idea is, so here's a beach ball floating on water. There's got to be something counteracting the weight of the ball, and so that's what we call the buoyant force. There's an upward force from the fluid, which is balancing out the downward weight force and allowing it to float on the water. If I add a little extra downward force on the ball with my hand, and the ball's still not accelerating now, right? I'm just holding it in equilibrium there. There's got to be a bigger upward force to counteract that extra downward force I've added with my hand, and therefore the buoyant force has gotten bigger. So the buoyant force is getting bigger as I shove more of the ball under the water. We all kind of have that intuition just by, playing around in pools. The idea of the buoyant force is, when you have an object that is really dense, it's going to sink. When you have an object that's not so dense, like a ball filled with air, it's going to float. And the reason it floats is because of a competition between the buoyant force and the weight force. If you let something go from rest, the weight force is what it is because the object has a certain gravitational attraction. And the buoyant force is either bigger than the weight force or it's less than the weight force. And if the buoyant force is bigger than the weight force, it's going to start accelerating upward. Now, of course, when it accelerates upward, there starts to become fluid drag because it's moving through a fluid, and then there's a third force. But at least it's going to tend to go up if it's got a big buoyant force compared to the weight, and it's going to tend to go down if the buoyant force isn't big enough to counteract the weight. So denser things are going to tend to sink. The origin of the buoyant force we talked about in lab, and it's actually pretty easy to get an intuitive grasp on. The origin of it just comes from the pressure. And we talked about the two properties, the key properties of the pressure. One is that, so here I'm imagining I put a sphere, maybe a brass sphere underwater, and maybe it's in the process of sinking right now, who knows. But in terms of the pressure is increasing as you go down. So what we're drawing here is little bits of force vectors that are being applied to little bits on the surface there. Okay, and so as we talked about earlier on in the class, much earlier, the force due to the pressure is always perpendicular to the surface. So on the sphere, it would be pointing inward towards the center of the sphere everywhere. And the pressure gets bigger as you go deeper in the fluid. So those force vectors on little bits of similar sized area are actually getting bigger. And the largeness of the up vectors compared to the smallness of the down vectors gives you an overall up force from the pressure from the fluid, right? And that's the source of the buoyant force. It's pushing up harder on the bottom upward than it is pushing downward on the top. Here, I think these images are from Giancali, so maybe they look familiar. One way to derive it simply, although you'll see we don't need to do it this way, is just to consider a very special shape of a cylinder. Let's say the top of it has an area A, and the top of it is a distance h1 below the surface. The bottom of it is a distance h2 below the surface, and we'll call the difference in those h's delta h. That's the height of the cylinder. And of course, the buoyant force here, the inward forces along the curved outside, which all point towards the axis of the cylinder, tend to cancel out. But we've got a smaller downward force on the top and a bigger upward force on the bottom. Those don't cancel out. And so the difference between those is going to give the buoyant force. So that's what we're going to calculate here. And let's use our knowledge of rho g h to figure out what the pressure is at each point. At the top, we have a pressure of rho of the fluid. That's given by rho F here, just to remind, because this might be made of brass. We might have a rho of brass too, but here we're talking about rho of the fluid. Rho G H2, if I want to calculate the pressure down here at the bottom, rho G H2 is the pressure at the bottom, and pressure times area is the force. So if I multiply rho G H2 times A, I get the force, which is upward on the bottom, and rho G H1 times A would be the downward force on the top. And now let's just factor out the common stuff there. We got a rho fluid, and we've got a G, and we've got an A that's common to all of it. And what's left is just H2 minus H1, which is delta H. And that is the height of the cylinder. And now with that there, the cross-sectional area of the cylinder times the height of the cylinder can be thought of as the volume of the cylinder. And now I can look at this expression and try to interpret it. What we've got is the volume of the interior of the object I've submerged. If I multiply that times the density of the fluid, right? If I multiplied the volume of the object times the density of the object, I'd get the mass of the object, because density is mass per unit volume. You multiply by volume, you get mass. If I had multiplied by the mass of the object itself, rho times V would be mass, but we're multiplying by rho fluid times V. That would be the mass that fits inside the cylinder. And, you know, in terms of Archimedes' principle, we would say that's the mass of the fluid displaced by the cylinder. And then when we multiply that mass times little g, m times g is a weight. So the interpretation of this is the weight of the fluid displaced. Okay, and that's Archimedes' principle. The buoyant force on an object immersed in a fluid is equal to the weight of the displaced fluid by that object. This seems like, well, okay, we calculated it for a cylinder. Who cares? What? Try doing that for a sphere. Well, it's actually, if you think about it the right way, it's easy to calculate for, or convince yourself of it for any shape object. And presumably this is the eureka moment that Archimedes had when he realized, you know, with just a couple of facts about pressure, it doesn't matter what the shape of the object is. So here's, I'm imagining maybe I've got a brass sphere or something like here, or a steel sphere. And I'm imagining what the pressure is at every point on the outside of that object, right? And of course, there's going to be a net upward force because the pressure is increasing as we go to lower parts of the object. So it's going to tend to be more up than down. What Archimedes realized is that if you just imagine replacing that solid object with just same shape of pure water or whatever the fluid is, right? Just replace it with the fluid. Because fluid exerts pressures on fluid, right? The fluid on the outside of this sphere of fluid is exerting inward pressure on the inside of the fluid. And it's exactly the same on each little area. That little force is going to be exactly the same as it is at every area on this solid object, because the pressure is exactly the same and the force is going to be in the same direction on that imagined sphere of water that fits inside the solid object. Now, unlike this solid object, if this is made of steel, of course, the thing's going to want to sink. So it's probably not in equilibrium, right? It would start accelerating downward if we let it go. Unlike that, this water is in equilibrium. The sum of the vertical forces on it have to balance. And what that means is the weight of this water must be balanced out by the buoyant force on that sphere of water. So the buoyant force in this case equals the weight of the water that fits inside the sphere. What Archimedes realized is that, look, the buoyant force over here is going to be exactly the same because it's due to that same pressure acting in the same directions on the same amounts on the surface of the object. So the buoyant force over here is the same as the buoyant force over here. And just by thinking about it, we realize that balances out the weight of the water that fits inside that object. So the buoyant force over here is equal to the weight of the water that fits inside the object, or it's usually said, you know, the weight of the fluid displaced by the object, how much fluid was pushed out of the way to make room for that object. But it's the same as how much fits inside the object. So that's Archimedes' principle, and presumably what Archimedes was thinking, you know, because it doesn't matter the shape of the object. This argument doesn't depend on this being spherical or cylindrical or anything like that. Questions about that? You have to be careful about it because, you know, we don't want the volume of the thing displaced. We don't want the mass of the fluid displaced. We want the weight. And so you've always got to think, okay, if I know the volume, I've got to figure out the mass of the water that would fit inside it and then multiply by little g to get the weight. We will do a worksheet problem shortly that involves things that are not completely submerged, like this log here. In this case, you know, most wood floats in water. And so this log, if you let it go from rest, is going to start accelerating upward. And then we have a fluid drag force. Eventually, it starts moving at constant velocity. But it rises and sits partially out of the water. So the idea is if it floats, it keeps moving upward. And as it starts to get out of the water, less of it is below the water. And that means the volume of the fluid displaced is less when it's sitting out of the water compared to when it's completely submerged. And that means the weight of the fluid displaced is less, and therefore the buoyant force is less. So it keeps going up until the buoyant force exactly balances out the weight force, and then it's in equilibrium, and that's the point at which it floats. Okay, we are working on a worksheet that boy, you got a long time ago. I think it was a week ago Monday, before our exam, is when it was posted on the website. We didn't start using it that day. So if you're on Zoom and you don't have a printed copy of this worksheet, or you haven't downloaded it already, look on the website, not this past Monday, but a Monday before that. That's when I posted it in the date there. And we've done a couple of problems, or at least we did the first problem. I think we did 2 problems on this worksheet already. And I've got one for anyone who needs one in the classroom here, or at least I've got a couple extras. We're given the density of ice. So here's an ice cube sitting in some water. Maybe it's another drink, but it's essentially equivalent to water. And you all have a pretty good idea. If you have a cube of ice, you know what fraction of it is going to float above the water. So maybe you have an idea of whether your answer will be seem to be right or not. So we got an ice cube, perfect cube of side 2.5 by 2.5 by 2.5 centimeters. We place it in water, and we want to know how far does the top of the ice cube stick out of the water. It's floating because when it was under the water, the buoyant force was greater than the weight force. So it starts rising until some of it sticks out of the water. Anybody in the classroom here need a copy? Oh boy, I don't know if I have that many copies, but I'll hand out what I have. Raise your hands again. Yes, it's this one with the water bridge on the front. If you've got that one. Oh, maybe. I'm confused. Maybe I messed up the printout or something. Well, we may have to, I'm certainly not going to go print it out now. So we may have to just go on the version that's up here, and you say, you certainly can just do it on your own paper. Sorry about that. I think what happened is I printed it out and I forgot to collate and staple it, since it was a multi-page thing. And then somehow they got separated, and I handed out the first one, but not the second one. Hopefully the version that's on the website shows it, but in any case, it's up here on the slide now. As you can imagine, right, that ice cube's in equilibrium. So our beginning point is to draw a free body diagram and say the sum of the vertical forces has to be 0 because it's not accelerating upwards or downwards. And you've got to think about what the buoyant force on that ice cube is. And it might help you, at least to start out, to say, draw a little picture, surface of the fluid, and let's say a distance x is sticking out of the water. So it floats at some distance x above the water. I didn't mean for this to be tilted here. Let's suppose a distance x sticks above the water, and that's what I want to find out, right? So you just imagine I know x, but I'm going to write everything down in terms of x, and hopefully I get an equation in terms of x when I balance those forces that allows me to solve for what x is. Notice that if the sides are length 2.5, then the amount that's below the water is it's 2.5 centimeters. So that would be 0.025 meters. Minus x would be how much is below water, and that's going to come into the volume of the fluid that gets pushed out of the way. So I'll give you a couple of minutes to think about that, and we'll do it together. There's always strange moaning sounds coming from the room in here. I'm just wondering if that is going to be a permanent feature of Olin Hall, like just there's some sort of fluid that's making noise in the pipes. And it doesn't seem like they're really doing construction, so hopefully we won't keep hearing those noises in the classrooms forever and ever. I guess I should also remind you that rho of water is 1,000 in SI units. It's 1 in grams per cc, but 1,000 in kilograms per cubic meter. Okay, let's try it together. Let me straighten up the camera. So again, I'm going to presume that it's sticking out of the water by some height x, and I want to determine what x is. Since this is 0.025 meters in height, the amount below the water, we'll see we need that, is 0.025 minus x. And now I'm going to do a free body diagram for that ice cube. Down, I've got whatever the mass of the ice cube is times little g. And upward, I've just got the buoyant force. And the buoyant force is due just to, the volume of the water that's pushed out of the way, right? We want the weight of the water that would fit in the part of this that's submerged. That's what Archimedes' principle says, the weight of the fluid displaced. So if I want to calculate the buoyant force, maybe I put this in a bad location. Rho ice is 917 in SI units. That was given on there. The buoyant force is the weight of the water that would fit in the size of the cube down here. So that's going to be 0.0, the area of the bottom is 0.025 times 0.025. I'm going to write that as 0.025. And the height of the part that's submerged is 0.025 minus x. Okay. That is the volume of the fluid displaced, right? What I've calculated is the volume of the box part that's underneath the water, right? It's 2.5 this way, it's 2.5 that way, and it's less than 2.5 in that direction. That's the volume of the fluid displaced. If you multiply the volume of the fluid displaced times the density of the fluid, this would be the mass of the fluid displaced. Archimedes' principle says we don't want the mass of the fluid displaced, we want the weight of the fluid displaced. And you multiply mass times little g to find out what the weight of that fluid would be. Okay. And that buoyant force has to balance out the weight force, right? The weight force is due to the entire ice cube. So I can get, since I have the density of ice, if I multiply that times the volume of the ice cube, that will give me the weight of the ice cube. So over on this side, I'm going to get a 0.025 cubed, that's the volume of the ice cube, times the density of ice. And that would give me the mass of the ice cube times little g. Okay, so I'm setting these two equal. That's m times little g on this side. So they've got to balance each other out because there's no net force. And there's my equation I'm going to solve for x. We can cancel out a 9.8. I guess we can cancel out these two factors of 0.025 against, I can just cancel that and put a 1 up there, right? Cancel two of those factors. And I think then I can just solve for x, right? Divide both sides by 1,000, and that's 0.025 minus x, and continue solving for x. The number I got, if you're coming along, is 2.1 millimeters, 0.00208 meters. 0.00208 meters, or about 2.1 millimeters. And that's, the numbers I've chosen here are supposed to reflect, it's pretty, 2 millimeters, that's pretty typical size ice cube, and that it floats 2.5 centimeters along a side, typical size ice cube, and that 2.1 millimeters floats above, at least doesn't violate my intuition, right? Ice cube doesn't float too much above the surface, but it does tend to stick above the surface a little bit. So that's a little bit of Archimedes' principle. Any questions on that one? Yes, Sarah. Right, so remember when I draw a free body diagram, I have to be clear about what the object is. And so here my object is the ice cube. And so we're going to consider the full gravitational weight force pulling down on that ice cube and the full buoyant force pushing up on the ice cube. Now the buoyant force, although it's being applied to the whole ice cube, is only due, according to Archimedes' principle, to the part that's submerged, right? We just have to think about the amount of fluid that got pushed out of the way. But the mass, of course, has to do with the entire volume of the ice cube. I think, let's just see, I think there's another problem that we're supposed to work on right now. Let's see, yes. Here it is, and I think this is both parts of it. So why don't you think about this one? Here is a cube of aluminum. Again, 2.5 centimeters on the side. You're given the density of aluminum there, 2,700 in SI units. Clearly it'll sink in water because it's more dense than water. And it's connected by a light string to a scale that reads in newtons. So one of those things that just detects what the tension in the string is. What does the scale read before I do anything funny with it? Just hang it from the scale. And then I submerge the cube in water. So it's not resting on the bottom of the little flask or cylinder that I've got it sitting in there. It's just suspended in the middle, but there is now a buoyant force on it. So it seems like in both these cases, A and B, I again want to draw a free body diagram, probably for the cube of aluminum in this case, and draw all the forces. In neither case is it accelerating, so the sum of the vertical forces will be 0, and hopefully I can solve for what the scale reads in those two cases. It's like a little tiny train blowing its whistle. Sorry, you guys at home can't hear what we're hearing in the room. Okay, so let's do A together, and we'll just try to modify the free body diagram when it gets submerged in the fluid. So here it's just sitting out in air, and I guess I should mention that when something's sitting in air, it is sitting in a fluid, and there is a tiny buoyant force from the fact that air is a fluid, and it's got a higher pressure at the bottom than it does at the top. Now, the density of air is about 1 in SI units compared to 1,000 for water. So it's a much smaller effect. And usually we ignore the buoyant force due to the fact that something is immersed in fluid of air at just, in normal room experiments. Okay, so ignoring that buoyant force from the air, we have the scales pulling up in the tension in the string, and then we've got mg going down. We're going to have to figure out what m is. We were given the volume, but we're also given the density so we can get the mass. Okay, and if I, just to go way back to how we set things up earlier, if I take plus y is up, and then I do the sum of the force y components has to equal m-ay. Ay is 0 in this case. So I get F scale minus mg equals 0 because Ay is 0. It's not accelerating along that direction. And therefore, these two things are equal. F scale, therefore, is mg. Mg, and m is the density of aluminum, 2,700, times the volume of aluminum, which is 0.025. I think it was the same dimensions. It was a perfect cube. So 0.025 cubed would be the volume in SI units, cubic meters. That's the mass of aluminum, and then I multiply by a little g to get mg. And so that should be the scale reading. I get 0.413 newtons. Okay, now slightly more interesting is B. When we dip it in water, the scale reading actually goes down. It weighs less. The same way when you get into a pool, you feel like you're light, right? Your feet don't have to hold you up with as much force down on the bottom of the pool when you're fully submerged or even partially submerged. So how am I going to change things in B? The only difference is the scale is still pulling up. That's what we're going to solve for. The only difference is there's also an additional buoyant force from the fluid it's being dipped in. I think water in this case, is that right? Dipped in water, yeah. So now my free body diagram looks like this. And therefore, the scale force will be equal to mg minus the buoyant force. Okay, we already figured out what mg is. It was 0.413 newtons. 0.413 newtons. Okay, let me just write it all the way. Plus FB equals 0. And therefore, F scale is mg minus FB. We already solved for mg before, so let's just utilize our work from before. Minus the buoyant force. And the buoyant force, according to Archimedes' principle, is the weight of the fluid that's displaced, or the weight of the fluid that fits in the object. That's the volume of the object, 0.025 cubed. It's fully submerged, so we take the full volume of the object. That's the volume of fluid displaced times the density of the fluid. Here we want 1,000 for the density of water. That's the mass of the fluid displaced, and mass times little g gives weight. So that's the weight of the fluid displaced. And when you subtract that off, it reduces it. I have 0.260 newtons. So it's less. You saw that, or you measured it in lab a little bit. Okay, any questions on those? Good, solid practice problem. Those of you who have gotten deep into the homework, you'll find that, there are some that are slightly more convoluted than that, but that's the basic idea. If you can just think in terms of rho VG for calculating those weights. And the big temptation is always to use the wrong rho, right? You don't want to calculate the buoyant force by using the density of the object itself. It's the density of the fluid that goes into that buoyant force. Okay. Strange that my slides didn't update, but no worries. Okay, so the next thing we're going to talk about is moving fluid. We've been talking about static situations where at the macroscopic level, there's no currents or anything. We're not going to talk too much about moving fluids, but one case that's sort of easy to get at fairly in a straightforward way is called continuity. And what that has to do with is when a fluid is flowing through a tube and the diameter of the tube changes as you move along the fluid, the tube, the fluid has to speed up or slow down to accommodate those changes. And that's because we can't, if I draw a little big cross-sectional area here and I say, what's the rate at which mass is crossing that? What's the change in mass that moves across it divided by the change in time? The rate at which mass is passing here better be the same as the rate at which mass is passing here, right? Because mass is flowing into this region here and it's flowing out over there. If it's flowing in faster than it's flowing out, then mass is going to be building up in that middle region. The whole thing's going to explode very quickly, right? So anytime you have something which is sort of an equilibrium situation like this, where you've just got fluid flowing down a tube like this, in order for mass not to build up, we've got to have the rate at which mass flows down the tube be constant at all points along the tube. Now, and because the tube has different diameters, presumably here, what that means is we're going to have the fluid moving with a greater velocity in the regions where it has a smaller cross-sectional area. And we want to know exactly what that relationship is. So the mass flow rate is the rate at which mass is flowing past a surface. And we are going to just demand that, if it doesn't do this, if the flow rate in is not equal to the flow rate out, that cannot last for very long. Something's going to break almost immediately if those aren't equal. So we're going to demand that the flow rate in equals the flow rate out. And let's think about how to rewrite the flow rate in terms of the velocity over here. If I think of an amount of time passing, right? And I say, over here in a certain amount of time, maybe 1 second, the fluid moves a distance delta x1 here. And in that same amount of time, the fluid moves a distance delta x2 over here in this thinner part of it. One way to calculate the mass flow rate is just to say, well, in that amount of time, I'm just going to see what sort of volume moves past that surface, whether it's the wide surface or the narrow surface. If I know the volume, then if I multiply by the density of the fluid, that'll give me the mass of the fluid that passed by that surface. And this is the amount of time that it did that in. Okay, so expressing that volume, the volume is sort of the volume of this cylinder that's shown right here, right? In time delta t, this is how far it moves. And therefore, the volume is A1 times delta x1. And over here, the volume is A2 times delta x2. Let's make those replacements for the volume. And if I multiply that volume that passed by the surface in time delta t, that would be, if I multiply by the density, that gives me the mass that flowed by in time delta t. So this is an expression that tells me about the rate at which mass is passing the surfaces. What we're after is the ratio of these deltas here. Notice that delta x1 over delta t is the amount of time it takes the fluid to move distance delta x1. So this is the speed of the fluid at position 1. And similarly, delta x2 over delta t is the speed of the fluid at position 2. We're further going to make the assumption that the fluid is incompressible. In other words, the density of the fluid doesn't change as it travels along the tube. Certainly that's going to be true for most liquids. It might not be true for a gas that's flowing at very high speeds. The gas can actually have huge changes in pressure, and sometimes that can change the density by quite a bit. We're going to assume the fluid is kind of like water. It's to a very good approximation, incompressible. And so the density of the fluid here is about the same as the density there. And so we'll cancel out those density factors. And when you do that and replace delta X over delta T with V, you get what's called the continuity equation for an incompressible fluid. And that just says the product of the cross-sectional area times the velocity is the same at all points along the tube. As the area gets smaller, the speed has to get bigger. Okay. And let's try a problem associated with that. I'm trying to do, well, I didn't want to do that. Let's see. Yeah, here we go. Let me share the screen again. So here's, I think it was problem 5 on the worksheet, but nobody seems to have it anyway, so you'll never know the difference. A syringe has a glass cylinder of inner diameter 1 centimeter. So the tube size opening that you're pushing that plunger thing down into has a diameter of 1 centimeter. And the needle has an inner diameter of 0.5 millimeter. I just made these numbers up, so maybe they're laughably off. I mean, 0.5 millimeter might be big for a needle. Maybe that would be super painful. If the plunger is pushed into the cylinder at a speed of 1 millimeter per second, again, I just, you know, if you're injecting a lot of fluid, I wouldn't want it going in too fast, so I just made that up. With what speed does the fluid exit the needle? It's going slowly in the wide part. How fast is it going in the narrow part? And again, the relationship we're going to use is A, cross-sectional area A times V is a constant. So it's the same at both parts of this. Essentially, we've got a tube here that's becoming extremely narrow. Okay, let's do the problem together. I tried to draw a, this doesn't look very much like a needle, but just a narrowing tube that is going from a 1 centimeter diameter to a 0.5 millimeter diameter. And A1 times V1 here has to equal A2 times V2 here, and we're given V1 in this region. We want to find V2 over there. So let's just plug in what we know. The cross-sectional area, it's a circular cross-sectional area, so I'm going to use pi r squared. We're given the diameter, so we have to divide by 2, and let's put it in SI units. 1 centimeter is 0.01 meters. We need to divide by 2. That gives us the radius and square it. So that's pi r squared times V1, and was it 1 millimeter per second? Yeah. V1 in SI units is going to be 0.001 meter per second. I'm trying to put everything in an SI units, right? That's 1 millimeter per second. And same thing over here. A2 is pi times 0. Well, let's see. This would be 1 millimeter. We need a half millimeter. So I'm going to put a 0 there and a 5. And then I've got to divide by 2 to get the radius and square that again times V2 and solve for V2. I get 0.4 meters per second. Which, you know, just putting it in the same units that it was given in, it was moving at 1 millimeter per second on this side. This is 400 millimeters per second. So it's a factor of 400 bigger in terms of the speed. And that's because there's a great narrowing of the cross-sectional area. Okay. Any questions on that one? Let's see if my reading response questions got on here. Yes, they did. So let's do a few reading response questions. And then if there's, you know, one question about homework or something, maybe we can do that and call it quits. And we'll start on the last chapter, which again, you know, this chapter took about 2 days. The last chapter, maybe a day and a half for the stuff that we're going to cover. We'll see how it goes. I'm in no rush to finish covering anything. We're good to go. When looking at the atmospheric pressure, when holding your finger over the end of a straw or hose and pulling up the water, you know, like you did when you were a kid, right? You fill up the straw and lift it up and then, you know, let it go somewhere else. How would you calculate the suction on your finger in regard to how much water is pulled out? In other words, how high you've pulled it up. Not sure. Let's draw a picture of this on the board. You know, the real question, or one thing you might ask yourself, is what do you mean by calculate the suction? We could calculate how much below atmospheric pressure the gas is just below your finger is, as opposed to the atmospheric pressure outside. And the greater the difference, the more your finger is going to be sort of forced into that void and sort of bubble out into the straw. But one way of answering that is to say, okay, I've got a vessel here with some water in it open to the atmosphere, and then I've got a straw going down in it, and the fluid is filling up the straw till very close to the top, and then I've got my finger over the top of the straw. So I've got a height of fluid there, and I would say here at the surface, of course, the pressure is 101.3 kilopascals. That's atmospheric pressure. It's going up, increasing pressure down there, and then it's back to 101.3 kilopascals when we're at a height that's the same as the height of the surface. It went up, and then it goes back down to atmospheric pressure here, and then it keeps decreasing as we go up. So if I've raised it to a height h, the difference in pressure between the surface and wherever the fluid is the difference in pressure we talked about, rho g times h. So the pressure is rho gh lower than atmospheric pressure up there. So the pressure right underneath my thumb is going to be 101.3 kilopascals minus rho of the fluid times g times whatever h is. Maybe h is 20 centimeters or whatever I've lifted up, you know, typical straw length. So it's going to be a little bit less than atmospheric pressure. That's one answer to what the suction is. And of course, you know, the pressure of, you know, things inside my body are used to pushing against the inward, you know, we're constantly being crushed by the atmospheric pressure and our body is sort of pushing outside. Anytime you lower the pressure on a little region of your skin, then your skin starts to bubble in that part, you know, because it's used to pushing out against all this pressure. Suddenly it says, oh, I can sort of bubble out freely into there. So your thumb is going to get sucked down in there a little bit because it's used to being in a region of higher pressure. Why can't a vacuum pump lift water that is more than 10 meters? And what are the multiple stages required to do that? Well, we talked about that experiment of lifting up fluid in a hose or trying to suck water out of your neighbor's pool. And we found that at about 10 meters, you start, the pressure goes down as you go. Maybe I shouldn't have erased this picture. Here's your pool. It's the same question, right? I've got a hose going up. Here it's at atmospheric pressure. Pressure's going down, 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 down. At some point, it reaches zero pressure. And if the fluid gets moved up at all, it's going to fall down because there's nothing from below to push up on it, right? Here I've got a higher pressure, so it can hold up a lot of fluid. Here I've got a little pressure, so it can hold up a little bit of fluid. Here I've got zero pressure. It can't hold up anything. You throw more fluid on top, it just lowers down because there's nothing to hold it up right there. So the idea is if you want to pump water up, without having looked at the book, I don't really know what they said, but you pump it up to a height of less than 10 meters, pretty substantial, a couple floors worth of height. And then, you could have the water, so you've got your pump, doing whatever it's doing there and pumping the water up here, and it comes out and you can have it flow into another container there. And you can pump it up further from there. And those would be an idea of like a crude set of stages, right? You have it flow out and then it's at atmospheric pressure again. And you can go up another 10 meters, have it flow out and fill up a vessel, then it's an atmospheric pressure again. And you can keep going like that. Since Archimedes' principle works better for objects that float, is there another principle for objects that don't float? No, Archimedes' principle applies equally well to objects that are neutrally buoyant or want to rise or want to sink underwater, because each one's displacing the same amount of fluid. So the weight of the fluid displaced is the same. I understand how pressure measurements can be derived from the change in height of the fluid, but not really how the fluid changes heights. I think I'm not exactly sure why I put this one in here, but I think the idea is thinking about that idea of the manometer, where you've got some fluid in a tube. This side maybe is open to the atmosphere and over here. And so you might blow into the side and want to know how high the pressure is here. Or maybe you suck on this side and you want to know how low the pressure is there. So if I blow into this side, and so I have some high pressure here, the fluid, of course, normally it wants to hang out at the same level on both sides because it's at atmospheric pressure here. It wants to go down and come up to atmospheric pressure there. But if I increase the pressure here, then what happens is this side goes down and this side goes up. That's a manometer. And by measuring the difference in the heights, you can figure out how much above atmospheric pressure is the region is on this side. Not really how the fluid changes heights. So by increasing the pressure here, I have increased the pressure at the surface of this fluid. That means it's that same increased pressure down here. So this is a high pressure. It's at a lower atmospheric pressure up there. So it's got to have some stuff above it to balance it out. In other words, if I'm at atmospheric pressure here, I have to go up to get to that increased pressure level there. I'm not sure if that answers the question, but that's an attempt. In problems, we're usually considering pressure at sea level. Obviously, if you start to rise above sea level, that atmospheric pressure decreases, but how drastic would the decrease be? I wasn't really sure about the numerics of it, so I looked up a picture, and this was just something I pulled off the web, but it's kind of interesting because it shows Mount Everest on there. You got to kind of think about how to read it. They wanted the height to be on the vertical axis for sort of intuitive reasons. So that means the pressure is on the horizontal axis, and we're following this blue curve here. And, so what they're saying is, here's the top of Mount Everest at this altitude, which is a little bit less than 10 kilometers, maybe 6 kilometers or something like that. We're above 50% of the atmosphere. And what that means is that the atmospheric pressure is going to be down by 50%. In other words, atmospheric pressure here is only going to be half of what it is at sea level. Here, we're above 90% of the atmosphere. It's going to be 10% of the pressure at sea level, and so on. So you can see at the peak of Everest, it looks like, you probably have about 30% of the normal atmospheric pressure or whatever, which is why people struggle so much with getting enough oxygen into their system at those great altitudes. So it does go down quite a bit, but I'm not sure if that answers that question. It's not a nice linear curve because of that changing density of the atmosphere as you go up. Once you get up high, you have to go up a lot higher to pass a significant amount of gas because the density is so low once you get up high in the atmosphere. That's it for chapter 10. So before Friday, read chapter 13, at least the sections that I asked about. I'm not sure if I asked you to read all the way through the end, but you're supposed to read the first collection of sections in chapter 13. Our goal is just to get that mental picture of moving molecules and how it relates to pressure and how it relates eventually later in the chapter to the ideal gas law.